Welcome to NEET 2016 Physics Solutions. Phase 2 exam held on 24th July. Planck's constant h, speed of light in vacuum c, and Newton's gravitational constant g are three fundamental constants. Which of the following combinations of these has the dimensional formula of length? Let's see the dimensional formula of the given quantities one by one. Planck's constant ml square t power minus 1, speed of light L t power minus 1, universal gravitational constant m power minus 1 L cube t power minus 2. We can go by option verification method or the derivation of the formula. So I feel the option verification method is easier and straight away. You see the first option, it is root hg by c power 3 by 2. When you substitute the given dimensional formulas in that, we will get the final answer to be L, that is the dimensional formula for length. Two cars P and Q start from a point at the same time in a straight line and their positions are represented by xp at plus bt square xq ft minus t square. At what time do the cars have same velocity? Let us see the displacement of car P. It is at plus bt square. We obtain velocity by differentiation with respect to time. So velocity of P is dx by dt, that comes out to be a plus 2bt. Similarly, velocity of car Q is obtained by differentiating displacement of Q, that comes out to be f minus 2t. Now since both the velocities are same, a plus 2bt equal to f minus 2t, that gives you t equal to f minus a by 2 times b plus 1. In the given figure, a equal to 15 meter per second square represents the total acceleration of the particle moving in clockwise direction in a circular path of radius 2.5 meter at a given instant of time. The speed of the particle is. When a particle is moving in circular path, it has two accelerations. One is a centripetal acceleration responsible for taking the particle into circular path by changing the direction of velocity continuously. The centripetal acceleration acts towards the center along the radius. That's why it is also known as radial acceleration. Another one is tangential acceleration, which is responsible for increasing the speed of the particle. So it is in tangential direction to the circular path. In a given circle, radius and tangent are always perpendicular to each other. So the centripetal acceleration and tangential acceleration are perpendicular to each other. As per the diagram, the total acceleration is acting at an angle 30 degrees to the radius. So we can write centripetal acceleration AC equal to A cos 30. From there we get it as 15 root 3 by 2 meter per second square. Centripetal acceleration is also written as Vt square by r, where Vt is tangential velocity, which we have to find now. So upon simplification we get Vt equal to root of AC into r, that comes out to be 5.7 meter per second. A rigid ball of mass m strikes a rigid wall at 60 degrees and gets reflected without loss of speed as shown in figure. The value of impulse imparted by the wall on the ball will be. As you can see from the diagram, a ball of mass m is hitting the wall with a velocity v, making an angle 60 with the normal. Since there is no loss of velocity, there is no loss of kinetic energy, so it can be taken as perfectly elastic collision. Then change in momentum will be taking place in a direction in which impulse acts during the collision. In the case of ball colliding with the wall, the impulse will be acting along normal, so the change in momentum will take place only along the normal. The initial momentum, that is before collision, is mv cos theta, that comes out to be mv by 2. Since there is no loss of velocity from the diagram, we can see the final momentum, that is after collision, is also equal to mv by 2. Now the change in momentum is mv by 2 minus of minus mv by 2, that comes out to be mv. A bullet of mass 10 gram moving horizontally with a velocity 400 meter per second strikes a wooden block of mass 2 kg, which is suspended by a light inextensible string of length 5 meter. As a result, the center of gravity of the block is found to rise by a distance 10 cm. Find the speed of the bullet after it emerges out horizontally from the block. Let us apply conservation of linear momentum for the collision between bullet and the block. m1u1 plus m2u2 equal to m1v1 plus m2v2. So it can be taken as 0.01 into 400 plus 2 into 0 equal to 0.01 v1 plus 2 v2. Here v1 is speed of the bullet after collision, v2 is speed of the block after collision. As it is given that the block rises to a height of 10 centimeters after collision, we can find v2 from there as v2 equal to root 2gh. That comes out to be 2 meter per second. Putting this value in the conservation of momentum equation, we get v1, that is speed of the bullet after the collision, to be 120 meter per second. Two identical balls A and B having velocities 0.5 meter per second and minus 0.3 meter per second respectively collide elastically in one dimension. The velocities of B and A after the collision respectively will be. The masses of colliding objects are equal and the collision is perfectly elastic collision. So in such a case, the velocities will be exchanged during collision. So B will have the velocity of A and A will have the velocity of B. So the velocities are 0.5 for B and minus 0.3 for A. A particle moves from a point minus 2i cap plus 5j cap to 4j cap plus 3k cap when a force of 4i plus 3j is applied. How much work has been done by this force? As you can see, both the initial position vector and final position vector are given. So the displacement vector of the particle r bar equal to r2 bar minus r1 bar. That comes out to be 2i minus j plus 3k. And the force applied is 4i plus 3j. Work done can be expressed as dot product of force vector and displacement vector. So upon simplification, we get the work done to be 5 joule. Two rotating bodies A and B of masses m and 2m with moments of inertia Ia and Ib. Ib being greater than Ia have equal kinetic energies of rotation. If La and Lb be their angular momenta, then you can see the moments of inertia are given to be Ia and Ib, and the second one has larger moment of inertia than the first one. Now let us see the relation between rotational kinetic energy, angular momentum and moment of inertia, that is given by k equal to L square by 2i. As kinetic energies are equal, we can write L square by 2ia equal to Lb square by 2ib. From there we get La by Lb whole square equal to Ia by Ib. Since Ib is greater than Ia, we get Lb greater than La. A solid sphere of mass m, radius r, rotating about its diameter. A solid cylinder of same mass and radius is also rotating about its geometrical axis with an angular speed twice that of the sphere. The ratio of their kinetic energies of rotation will be. Moment of inertia of solid sphere about its diameter is 2 by 5 mr square. Moment of inertia of a solid cylinder about its geometrical axis is 1 by 2 mr square. The angular velocity of solid cylinder is given to be twice that of the solid sphere. Now coming to the rotational kinetic energy, it is half I omega square. Since we need to find the ratio of rotational kinetic energies, we can write k solid sphere by k solid cylinder equal to I solid sphere by I solid cylinder multiplied with omega solid sphere by omega solid cylinder whole square. By putting the values, we get the ratio to be 1:5. A light rod of length L has two masses m1 and m2 attached to its two ends. The moment of inertia of the system about an axis perpendicular to the rod passing through the center of mass will be. As you can see from the diagram, let us say C is the center of mass of the system of two particles. A center of mass of two particle system divides the distance between the two particles in the inverse ratio of their masses. So we can see R1 equal to m2L by m1 plus m2. R2 equal to m1L by m1 plus m2. The moment of inertia of a multi-particle system is I equal to m1r1 square plus m2r2 square plus so on mnrn square. Since here two particles are present, we can write the two terms m1r1 square plus m2r2 square. Upon simplification, we get the moment of inertia to be m1 m2 by m1 plus m2 into L square. Here m1 m2 by m1 plus m2 is known as reduced mass of the two particle system. Starting from center of the earth having radius capital R, the variation of g is as shown by. Let's divide the problem into three parts: inside the sphere, on the surface of the sphere, and outside the sphere. Inside the sphere, since earth is taken to be a solid sphere of uniform density, we can write acceleration due to gravity as gm by capital R cube into small r. So it is directly proportional to small r. Outside the sphere, we can consider earth to be a point mass with its complete mass located at the center of the sphere according to Newton's shell theorem. So the formula should be that of a point mass, that is gm by r square. On the surface of the sphere also it can be taken as point mass. So it is gm by r square. So inside the sphere, g is proportional to distance of consideration. Outside the sphere it is inverse square relation. So the correct option is second graph. A satellite of mass m orbiting the earth of radius capital R at a height h from its surface. The total energy of the satellite in terms of g0, the value of acceleration due to gravity at the earth's surface is. The total energy of a satellite orbiting the earth is given by the formula minus g capital M small m by 2r, where capital M is mass of the earth. This energy is negative to indicate that the solar system is a closed system. The satellites are bound to planets and planets are bound to sun. Acceleration due to gravity on the surface of the earth is given by g0 equal to gm by r square. From there gm equal to g0 into r square. As the formula is expressed in terms of small g, we can replace capital G capital M in the original formula to get total energy as minus mg0 r square by 2 times r plus h. Here small r is radius of the orbit of the satellite, which can be written as sum of radius of the earth and height of the satellite. A rectangular film of liquid is extended from 4 cm by 2 cm to 5 cm by 4 cm. If the work done in this process is 3 into 10 power minus 4 joule, the value of surface tension of the liquid is. You can see the initial area of the film is 4 by 2, that is 8 cm square. The final area of the film is 5 by 4, that is 20 cm square. Work done is given to be 3 into 10 power minus 4 joules. So the work done in increasing the surface area of a soap film is given by surface tension into increase in surface area. Here the surface area increase has to be doubled because the soap film has two surfaces. From here, by putting the values given, we get surface tension equal to 1 by 8, that comes out to be 0.125 Newton per meter. Three liquids of densities ρ1, ρ2, ρ3 with ρ1 greater than ρ2 greater than ρ3 having same value of surface tension rise to same height in three identical capillaries. The angles of contact are θ1, θ2 and θ3. Then the relation between them is, as we know, the surface tension of a liquid by capillary rise method is given by the formula h equal to 2t cos theta by r rho g, where h is the height to which the liquid rises, t is surface tension of the liquid, r is radius of the capillary tube, rho is the density of the liquid, g is acceleration due to gravity, and theta is angle of contact. According to the given condition in the question, h is proportional to cos theta by rho. As the liquids rise to the same height in all the three capillary tubes, we have h1 equal to h2 equal to h3. So cos theta 1 by rho 1 equal to cos theta 2 by rho 2, that is also equal to cos theta 3 by rho 3. As it is given that rho 1 is greater than rho 2 greater than rho 3, we get cos theta 1 is greater than cos theta 2 greater than cos theta 3. We know cos theta is a decreasing function, that is, as the value of theta increases, cos theta decreases. Another point here is, as the liquid is rising in the capillary tube, the angle of contact should be acute angle. That means it should be lying between 0 and 90. So the correct option is 2. Two identical bodies are made up of materials for which the heat capacity increases with temperature. One of these is at 100 degrees centigrade and while the other is at 0 degrees centigrade. If the two bodies are brought in contact, then assuming no heat loss to the surroundings, the final temperature will be. Let us say the given condition, the heat capacity increases with the temperature. So the heat capacity of the body at 100 degrees centigrade is more than that of the heat capacity of the body at 0 degrees centigrade. When the two objects are combined with each other, definitely the temperature should be greater than 50 degrees centigrade. So the option is second one. A body cools from a temperature 32 to 2T in 10 minutes. The room temperature is T. Assuming that Newton's law of cooling is applicable, the temperature of the body at the end of next 10 minutes will be. As Newton's law of cooling is applicable, let us write the formula dt by dt equal to minus b times T minus T naught. Here dt by dt is rate of cooling, T is average temperature, T naught is the room temperature. So when we apply the formula for the first 10 minutes, it is 3T minus 2T by 10 equal to minus b times 3T plus 2T by 2 minus T. That comes out to be T by 10 equal to minus b times 1.5T. Then when I apply the formula for the next 10 minutes, it is 2T minus x by 10 equal to minus b times 2T plus x by 2 minus T. That is 2T minus x by 10 equal to minus b times x by 2. When you take the ratio of the two expressions, we get C equal to 3 by 2T. 1 mole of an ideal monoatomic gas undergoes a process described by the equation PV power 3 equal to constant. The heat capacity of the gas during this process is. Since it is given to be monoatomic ideal gas, gamma of monoatomic ideal gas is 5 by 3. The heat capacity of a thermodynamic process described by PV power x equal to constant is given by C equal to R by gamma minus 1 plus R by 1 minus x. As the given question goes, in the place of x we can write 3 and in the place of gamma we can write 5 by 3. Upon simplification we get a specific heat capacity for the process is R. The temperature inside a refrigerator is T2 degree centigrade and the room temperature is T1 degree centigrade. The amount of heat delivered to the room for each joule of electrical energy consumed ideally will be. Since it is a refrigerator, let us see coefficient of performance of refrigerator represented with beta given by T2 by T1 minus T2. Here capital T represents absolute temperature. Converted into centigrade scale, we can get T2 plus 273 by T1 minus T2. Now the quotient of performance also can be defined as heat absorbed by the engine to work done on the engine. Work done is nothing but energy consumed by the engine. So we can write beta equal to Q2 by W. Since it is 1 joule of electrical energy consumed, we get beta equal to Q2. Now heat delivered to the room is nothing but Q1, which can be written as Q2 plus W, that is Q2 plus 1. Upon simplification we get the heat delivered to the room equal to T1 plus 273 by T1 minus T2. A given sample of an ideal gas occupies a volume V at a pressure P and absolute temperature T. The mass of each molecule of a gas is m. Which of the following gives the density of the gas? Since the gas is ideal, we can apply ideal gas equation, that is PV equal to nRT, where n is number of moles of the gas. Here the problem is framed in terms of number of molecules. So we can write the ideal gas equation also as PV equal to capital N into KT, where capital N is number of molecules of the gas. From this equation we can write N by V equal to P by KT. Since we are asked to calculate density of the gas, it is total mass per unit volume. So the total mass will be N into mass of each molecule, that is Nm by V. So which can be written as N by V into M. So N by V can be written as P by KT. So the final answer is Pm by KT. A body of mass m is attached to the lower end of a spring whose upper end is fixed. The spring has negligible mass. When a mass of m is slightly pulled down and released, it oscillates with a time period of 3 seconds. When the mass m is increased by 1 kg, the time period of oscillation becomes 5 seconds. The value of m in kg is. As we know, the time period of a oscillating spring is given by the formula T equal to 2 pi root m by k, where m is mass of the block and k is spring constant, also known as force constant. The initial time period is 3 seconds, so we can write 3 equal to 2 pi root m by k. The final time period is 5 seconds. We can write 5 equal to 2 pi root m plus 1 by k as mass is increased by 1 kg. Now taking the ratio and simplifying, we get m equal to 9 by 16 kg. The second overtone of an open organ pipe has the same frequency as that of the first overtone of a closed pipe of length L meter. The length of the open pipe will be. Let the length of the open pipe be L0. Then the frequency of second overtone of open pipe is F0 equal to 3V by 2L0. Similarly, frequency of first overtone of closed pipe is Fc equal to 3V by 4L. Since these two frequencies are equal, we can write F0 equal to Fc. From there we get L0 equal to 2L. An electric dipole is placed at an angle 30 degrees with an electric field of intensity 2 into 10 power 5 Newton per Coulomb. It experiences a torque equal to 4 Newton meter. The charge on the dipole, if the dipole length is 2 centimeters, is. As we can see, intensity of electric field is 2 into 10 power 5 Newton per Coulomb. Torque acting on the dipole when it is placed in uniform electric field is tau bar equal to P bar cross E bar, that is Pe sin theta. From there we get P equal to tau by E sin theta, which comes out to be 4 into 10 power minus 5 Coulomb meter. Then the electric dipole moment can be written as the product of one of the charges and the separation between the charges. So from there we get Q equal to 2 millicoulomb. A parallel plate capacitor of area A, plate separation D and capacitance C is filled with 4 dielectric materials with dielectric constants K1, K2, K3 and K4 respectively as shown in figure. If a single dielectric material is to be used to have the same capacitance C, then the dielectric constant of that single material should be. Capacitance of a parallel plate capacitor with a dielectric is given by C equal to K times epsilon naught A by D, where K is the dielectric constant of the material. As the arrangement shown in the figure, we can see K1, K2, K3 are connected in parallel. So we can write the capacitance formulas for respective capacitors. C1 equal to K1 times epsilon naught A by 3 D by 2. On similar lines, we can write the formula for C2, C3 and C4. As C1, C2, C3 are in parallel, the effective capacitance is C1 plus C2 plus C3. This combination is connected in series with C4. So the final value comes out to be 1 by C equal to 1 by C parallel plus 1 by C4. Upon simplification, we get 2 by K equal to 3 by K1 plus K2 plus K3 plus 1 by K4. The potential difference VA minus VB between the points A and B as shown in the figure is. As seen from the diagram, it is a part of circuit between points A and B. There are resistors 2 ohms and 1 ohm and a battery 3 volt. A current of 2 amperes is flowing from A to B. By applying Kirchhoff's voltage law, we can write VA minus IR, that is 2 into 2, minus drop due to the battery minus 3 volt and minus drop due to resistance current, that is 2 into 1 minus VB equal to 0. From there we get VA minus VB equal to 9 volt. A filament bulb of power 500 watt and voltage 100 volt is to be used in a 230 volt main supply. When the resistance R is connected in series, it works perfectly and the bulb consumes 500 watt. The value of resistance to be connected is. As it is given that the bulb is consuming rated power, so rated current is flowing through the bulb. The rated current is given by I equal to P rated by V rated, that comes out to be 5 ampere. The resistance of the filament of the bulb is given by R equal to V square by P, that is 20 ohm. Now the current flowing through the circuit, that is equal to the current flowing through the bulb, that is 5 ampere. We can write the formula for current as I equal to V by R total. Here there is an external resistance capital R and resistance of the bulb small r connected in series. So the total resistance is 20 plus R. From there we get the resistance is 26 ohm. A long wire carrying a steady current is bent into a circular loop of 1 turn. The magnetic field at the center of the loop is B. It is then bent into a circular coil of n turns. The magnetic field at the center of this coil of n turns will be. Magnetic field at the center of a circular loop is given by mu naught In by 2R, where n is the number of turns, R is radius of the loop. Since both the loops are bent from the same wire, we can see their circumferences should be equal. So 2 pi R equal to n times 2 pi R dash. From there we get R equal to nR dash. So the magnetic field at the center of the loop is mu naught In by 2R, and the magnetic field at the center of the second loop is mu naught In by 2R dash. Replacing R dash with R, we get B dash equal to N square B. A bar magnet is hung by a thin cotton thread in a uniform horizontal magnetic field and is in equilibrium state. The energy required to rotate it by 60 degrees is W. Now the torque required to keep the magnet in its new position is. Work done in rotating a bar magnet in a uniform magnetic field is given by the formula W equal to mb times cos theta 1 minus cos theta 2, where capital M is the magnetic moment of the bar magnet, B is the magnetic field induction. So here the initial value of angle is 0 and the final angle is 60. Upon simplification we get work done equal to mb by 2. Now the torque acting on the bar magnet is given by the formula mb sin theta. Here theta is 60, so it is root 3 by 2 mb. By replacing mb from both equations we get a tau equal to root 3 w. An electron is moving in a circular path under the influence of a transverse magnetic field 3.57 into 10 power minus 2 Tesla. If the value of E by m is 1.76 into 10 power 11 coulomb per kg, the frequency of revolution is. The time period of revolution of a charged particle in a uniform magnetic field is given by T equal to 2 pi r by V. That is 2 pi by V into radius of the circular path can be written as mv by bq. So upon simplification we get it as 2 pi by b times q by m. Now the frequency is reciprocal of time period. So it is f equal to 1 by t b times q by m by 2 pi. Upon substituting the numerical values we get the frequency to be 10 power 9 Hz, that is 1 gigahertz. Which of the following combinations should be selected for better tuning of an LCR series circuit used for communication? Better tuning of LCR series circuit is decided by the quality factor of the circuit, which is given by the formula 1 by R root L by C, where R is resistance, L is inductance and C is capacitance. So by substituting the values of the 4 options, we find in the third option the quality factor is maximum, that is 22.77. So the correct option is 3. A uniform magnetic field is restricted within a region of radius small r. The magnetic field changes with time at a rate of dB by dt. Loop 1 of radius capital R, which is greater than small r, encloses the region of small r, and another loop of radius capital R is outside the region of the magnetic field as shown in figure. Then the EMF generated is. As we can see from the diagram, there is magnetic field changing only in loop 1. There is no magnetic field in loop 2, so there is no EMF induced in loop 2. Coming to loop 1, E1 equal to minus d phi by dt, that is minus d by dt of B into A. Since A is constant, I can write it out of differentiation. So it comes out to be minus pi r square dB by dt. The potential difference across resistance, capacitance and inductance are 80 volt, 40 volt and 100 volt respectively in a LCR series circuit. The power factor of the circuit is, as we can see from the phasor diagram, resultant voltage or supply voltage is given by root of VR square plus VL minus VC whole square. That comes out to be 100 volt. Now the power factor of a circuit is given by the formula R by Z, that is cos phi. Multiply and divide with current, you get IR by IZ, that is VR by V, that comes out to be 80 by 100, that is equal to 0.8. A 100 ohms resistance and a capacitor of 100 ohm reactance are connected in series across a 220 volt source. When the capacitor is 50% charged, the peak value of displacement current is. Displacement current and conduction current both are same. So as we can see from the charging of capacitor, instantaneous charge equal to final charge times 1 minus e power minus t by RC. From there we get t equal to RC log 2. Now the current obtained as the differentiation of charge is I equal to capital I e power minus t by RC, where capital I is the maximum value or peak value of the current. The peak value of current is independent of time. At any given point of time it is I equal to V by R, that comes out to be 2.2 ampere. Two identical glass equiconvex lenses of focal length f each are kept in contact. The space between the two lenses is filled with water. The focal length of the combination is. The focal length of a lens is given by lensmaker's formula 1 by f equal to mu minus 1 of 1 by r1 minus 1 by r2. Here mu is refractive index of the material of the lens. R1 and R2 are radii of curvature. Since here it is an equiconvex lens, R1 equal to R2, so the focal length comes out to be 1 by R. Then the two lenses are kept in contact and the space between the two lenses is filled with water. So effectively there are three lenses in contact with each other. The effective focal length is given by 1 by f equal to 1 by f1 plus 1 by f2 plus 1 by f3. Here two lenses are equiconvex lenses. The middle lens formed by water is concave lens. So by substituting the values, we get effective focal length equal to 3f by 4. An air bubble in a glass slab with refractive index 1.5 is 5 cm deep when viewed from one surface and 3 cm deep when viewed from the opposite face. Find the thickness of the glass slab. Let T be the thickness of the glass slab and X be the actual depth measured from the top of the slab. The apparent depth is given by d apparent equal to d by mu. So that is 5 equal to x by 1.5, that implies x equal to 7.5 cm. Apparent depth from the opposite surface is d apparent equal to d by mu again. This time it is 3 equal to t minus x by 1.5. That implies t minus x equal to 4.5, so t equal to 12 cm. An interference pattern is obtained with two coherent light sources of intensity ratio n. In the interference pattern, the ratio Imax minus I minimum by Imax plus I minimum will be. Intensity ratio of two light sources is given to be I1 by I2 equal to n. Then the maximum intensity Imax equal to root I1 plus root I2 whole square. That is, upon simplification we get I2 times root n plus 1 whole square. On similar lines, minimum intensity is root I1 minus root I2 whole square. That is I2 times root n minus 1 whole square. When you take the ratio, it is 4 root n by 2 times n plus 1. That comes out to be 2 root n by n plus 1. A person can see clearly objects only when they lie between 50 cm and 400 cm from his eyes. In order to increase the maximum distance of distinct vision to infinity, the type and power of the correcting lens the person has to use will be. As per the given data, object distance u equal to 400 centimeter, that is 4 meter. Image distance v is infinity. Applying lens formula 1 by v minus 1 by u equal to 1 by f, we get f equal to minus 4 meter. Since the focal length is negative, the lens should be concave lens, and the optical power of the lens is reciprocal of focal length taken in meter. That comes out to be 0.25 diopter. A linear aperture whose width is 0.02 cm is placed immediately in front of a lens of focal length 60 cm. The aperture is illuminated normally by a parallel beam of wavelength 5 into 10 power minus 5 cm. The distance of the first dark band of diffraction pattern from the center of the screen is. Since the aperture is placed immediately in front of a convex lens, it can be taken as Fraunhofer diffraction. The condition for first dark band in diffraction pattern is a sin theta equal to m lambda, here m is 1. Since we can apply small angle approximation, I can replace sin theta with tan theta. So lambda equal to 0.15 centimeter. Electron of mass m with de Broglie wavelength lambda fall on a target in an X-ray tube. The cutoff wavelength lambda naught of the emitted X-rays is. The de Broglie wavelength of an electron can be written as lambda equal to h by p, where p is momentum of the electron, which also can be written as root of 2m ev, where v is the applied potential difference. Squaring it on both sides, we get lambda square equal to h square by 2m v. From there, v equal to h square by 2m e lambda square. Now the cutoff wavelength, also known as the minimum wavelength of the X-ray tube, is lambda naught equal to hc by ev. By substituting the value of v in this given expression, we get lambda naught equal to 2mc lambda square by h. Photons with energy 5 electron volt are incident on a cathode C in a photoelectric cell. The maximum energy of emitted photoelectrons is 2 electron volt. When photon of energy 6 electron volt are incident on C, no photoelectrons will reach the anode A when the stopping potential of A relative to C is. Let us apply Einstein's photoelectric equation E equal to 5 plus EV naught, where E is energy of incident radiation, phi is work function, V naught is the stopping potential. By substituting the given values, we get work function of the metal to be 3 electron volt. Now the energy of incident radiation is 6 electron volt, and the condition is the electrons released from the metal surface should not reach the anode. That means the stopping potential applied should be equal to the maximum kinetic energy of the released electron, which is 3 electron volt. So the answer is minus 3 volt. An electron in a hydrogen atom jumps from the third orbit to second orbit. It emits a photon of wavelength lambda. When it jumps from fourth orbit to third orbit, the corresponding wavelength of the photon will be. The wavelength of light emitted by hydrogen atom during electron transition is given by 1 by lambda equal to r of 1 by n initial square minus 1 by n final square, where lambda is the wavelength and r is Rydberg constant. For the first transition of the electron from third to second orbit, we can write 1 by lambda equal to r of 1 by 4 minus 1 by 9, that is 5r by 36. For the second transition of the electron from fourth orbit to third orbit, 1 by lambda dash equal to r of 1 by 9 minus 1 by 16, that is 7r by 144. When you take the ratio, we get lambda dash equal to 20 by 7 lambda. The half-life of a radioactive substance is 30 minutes. The time in minutes taken between 40% of decay and 85% of decay of the same radioactive substance is. The half-life of the substance is given to be 30 minutes. Time taken for x% of the substance to decay is given by 1 minus 1 by 2 whole power T by T into 100, where small t is the time of concentration and capital T is the half-life of the material. We are asked to calculate the time between 40% decay and 85% decay, writing the formula for 40% and 85%. Putting the given values in the expression, we get 1 by 2 whole power T1 by T equal to 0.6, 1 by 2 whole power T2 by T equal to 0.15. Taking the ratio of the two expressions, we have T2 minus T1 equal to 60 minutes. For a C transistor amplifier, the audio signal voltage across the collector resistance of 2 kilo ohm is 4 volt. If the current amplification factor is 100 and base resistance is 1 kilo ohm, then the input signal voltage is. As the transistor is in common emitter mode, input is base terminal and output is collector terminal. Given current amplification factor beta equal to 100, then the ratio of resistances in the output and input circuits is 2. Voltage gain of the amplifier Vg can be written as output voltage by input voltage, that is collector voltage by this voltage, which can be written in turn as a ratio of output to input currents to output to input resistances. So that is beta times Rc by Rb, that is equal to 200. Now voltage gain of the amplifier Vg equal to output voltage by input voltage, that is 200 equal to 4 by Vb. From there Vb equal to 20 millivolt. The given circuit has two ideal diodes connected as shown in figure. The current flowing through the resistance R1 will be, as you see the circuit, R1 and R3 are 2 ohm resistors and R2 is 3 ohm resistor. Now D1 is reverse biased and D2 is forward biased. Since the diodes are ideal, an ideal diode offers zero resistance in forward bias and infinite resistance in reverse bias. So if you redraw the circuit by considering these things, we can see R1 and R3 both 2 ohm resistors are connected in series to 10 volts battery. So the effective current through the circuit is 2.5 ampere. What is the output Y in the following circuit when all the three inputs A, B, C are first 0 and then 1? As we see, P is a AND gate. The output is high only when both inputs are high. And Q is a NAND gate. Its output is high only when at least one of the inputs is low. The output of P is A dot B while the output of Q is P dot C whole bar. Now let us see when all the inputs are 0. We get Y equal to A dot B dot C whole bar, that comes out to be 1. And when the all inputs are 1, the situation is reversed. So the output is 0.